Hello, this is Mr. Mack. And in this particular talk, we're going to talk a little bit about conic sections. And specifically, the conic section that is called the parabola. So first of all, what do we mean by conic sections? Traditionally, conic sections was a term that was used to talk about the curves that you would get when you intersect a plane with a cone. Now, this is two-dimensional, but it's a three-dimensional rendering, or it's a two-dimensional rendering of some three-dimensional concept. The idea here is that you have a cone. Actually, in mathematics, the cone extends up to be a reverse one on top. And then what we've got here is pictures of what you would get if you sliced this cone in different ways. Now, if you took a plane and you went straight across the cone, you would get a circle. So the circle is one of the conic sections. Now, if that plane actually was cut at an angle, but you cut all the way through the cone, you would get something that would be maybe an elongated circle. We call that an ellipse. Now, if your plane actually was parallel to one side, in other words, see this cut right here is parallel to this side of the cone, then you would only get one loop of the cone, and that slice would be a parabola. Now, that is what we're planning on talking about today. And then if you turned the plane so that it was cutting through both loops like this, you would get a piece up here and a piece down here, and we call that a hyperbola. So the four conic sections are circle, ellipse, parabola, and hyperbola. Today, however, we're going to deal basically with the parabola. Now, the Greeks defined parabolas to be the set of all points. Let's see, let me just go ahead and write this. Parabolas. It's the set of all points equidistant. That's just a big word. That means the same distance from a given point and a given line. Now, this given point has a name. It is called the focus. And the given line has a name. It's called the directrix. Now, a picture of the parabola, let's just move this down out of the way. A picture of the parabola looks something like this. Notice we have the directrix is this line, and the focus is this point. Now, a point that's on the parabola would be the same distance away from the directrix as the focus. Let's look at some points. If you looked at this point right here, notice this is the distance from that point to the directrix, and this is the distance from that point to the focus. Pick another point here that they haven't shown us. This would be the distance from the point to the directrix, and this would be the distance of the point from the point to the focus. And we could even go points beyond here. This is the distance from the point to the directrix. This is the distance of the point to the focus. And so then all of these points end up being the points of the parabola. Now, notice that the vertex point, that's this point right here, is halfway between the directrix and the focus. Now, we ordinarily say, or I was taught when I was young, to believe that this distance right here, the distance from the vertex to the directrix and the distance from the vertex to the focus are p. Now, if if the parabola is opening up, we say that p is positive, and so the distance from the vertex to the focus is p. So p is equal to the distance from vertex to focus. It's also the distance from the vertex to the directrix. And if p is negative, then of course the parabola is opening downward. Okay, now this isn't all that we're dealing with, however, though, because let's see if I can do this. Oops, don't want to do that. Here we go. Just group all of those together. We could actually turn this on its side. Let's move that up a little bit, move this down. There we go. Now you can see it. If we have we could have a parabola on its side as well. Now, at this particular point, you may be saying, well, Mr. McFarland, if you did that, you wouldn't have a function. And that's true. A parabola opening right or opening left is not a function, but it turns out that it is the inverse of a parabolic function. And so we have one equation that you learned before. This is vertex form for a parabola. Y is equal to a times x minus h squared plus k. This was vertex form for a parabola, and you learned things like if a was positive, the parabola is opening up. If a is negative, the parabola is opening down. But what I'd like to focus on right now is this is the quadratic function. In other words, we have x as the input and y is the output. And for each x, there's exactly one y. Now, there are a couple of different x's that give us the same y, but every x has only one y. Now, the equation for the quadratic relation that is actually not a function, in other words, the parabolas on their side, if you will, are x is equal to a times y minus k squared plus h. And in this case, we have still the same kind of thing going on, but it's on its side rather than on the top. Now, let's take a look at the at these equations in a little more detail. I'm going to go to the next screen, and I'm going to get rid of my picture of the conic sections here. How can I get rid of it? Oh, okay, I'll just throw it down here. It wants to bounce. Well, maybe not. Maybe it's not bouncing. Yeah. Oh, yeah, I guess it is bouncing. Go down. Go down. Go down. There we go. And now we can go up, and it's gone. All right. But we're going to take a look at this again. Now, if we have there we go. Okay, let's turn this one. I'm having trouble here again. Okay, if we put this one on its side like this, then here we go. This one, the vertex form for the equation is y is equal to a times x minus h squared plus k. Now, what do we know about this parabola? First of all, we know the vertex is at the point HK. We know the axis of symmetry is the line x equals h. Now, we also know that when A is positive, the parabola opens up or upward. And when A is negative, notice what I wrote when I said A is negative. I wrote A is less than 0. It opens downward. Now, a little bit more here. There is a line parallel to the directrix that contains the focus and connects 2 points on the parabola. And this line is called the latus rectum. Latus-rectum. The latus rectum. It's a line containing the focus joining 2 points, parallel to the directrix, and joining 2 points on the parabola. Now, it turns out that the length of the latus rectum, and this is what they'll usually ask you, the length of this is equal to the absolute value of 1 over A. See, if A is positive, if A is negative, we get rid of that negative. But in other words, the reciprocal of A is the length of the latus rectum. Now, is there anything else that we need to do about the quadratic function? Oh, yes. Now, remember I mentioned that P was the distance from the vertex to the focus. It's also the distance from the directrix to the vertex. P is going to be equal to 1 over 4A. So you can find the distance from the directrix to the vertex and the distance from the vertex to the focus if you know the value P, and notice that the directrix is perpendicular to the axis of symmetry. And so basically what we're going to do mostly is we're going to build these parabolas off of the vertex, and we're going to build them off of that and off of P here. So those are going to be the two important pieces of knowledge that we have for these quadratic functions. Now, one more thing. Parabolas curve, gosh, I can do this. Parabolas curve towards their focus and away from the directrix. If you look at this parabola here, notice that its curve is towards the focus. In other words, its curve is this way. Here's the focus. And it's curving away from the directrix. Here's the directrix. And as you move out, you're seeing that it's curving away from it. So with that information, you should be able to build an equation for a parabola if you're given information about the the vertex and P, or if they give you the length of the latus rectum, realize that you can use this formula to find what P is and then use that and so forth like that. Now, what does this mean in relation to the quadratic relation? Now, the equation for the quadratic relation is x is equal to a times y minus k squared plus h. Now, in this particular case, notice that h is associated with x and k is associated with y in both cases. So the vertex of this parabola is going to be the point hk again. Notice, though, that the part inside the binomial squared with y is going to be the y value, not the x value. The axis of symmetry is going to be y equals k. Now, when a is greater than 0, the parabola is going to open to the right. Oops, where did we go? To the right. And when a is less than 0, the parabola is going to open to the left. Now, it's still true. We still have, oops, put this down. We still have the lattice rectum. This time, the lattice rectum is here. Notice that it's still parallel to the directrix. It still goes to the focus. It still joins 2 points on the parabola curve. Its length is still the absolute value of 1 over a. Also notice that p now is the distance along the axis of symmetry, again, from the vertex to the focus, and also from the directrix to the vertex. But the axis of symmetry is horizontal, so So that's the way. And yes, then the parabola, again, still is curving towards the focus and away from the directrix. Now, that is the information that you need to be able to do these problems. And I'm going to do solution videos with some of them. And I think that pretty much takes care of it. So I'm going to end the concept video for parabolas right here. We're done.